We have seen in the previous class the relation of distance with potential with respect to a source charge. There is a source charge Q at certain distance r. At this point P, the potential V is equal to Coulomb's constant 1 upon 4 pi epsilon naught and Q, and here is R. This is what we have derived in the previous class. Is it clear to you? So this is, if we change R, then there is no change in the value of Q. It's a constant. This is a constant. This is a constant. This is a constant. So we can say V is proportionate to 1 upon R. So V is proportionate to 1 upon R. Now what is E proportionate to? E has the equation E is equal to 1 upon 4 pi epsilon naught Q upon R square. So this is proportionate to R to the power minus 2. That is 1 upon R square, and this is 1 upon R. Is it clear? Now if you make a graph of it, what should be the shape of that graph? With this you can make out, if we make R 3 times, if we increase R 1, 2, 3 times, which will decrease more? 3 times, the potential has decreased 1 upon 3, and what happens to electric field? It will decrease by 1 upon R. R we have made 3, so this is 1 upon 3, and this is 1 upon 3 to the power 2, that is 1 upon 9. So which is depleting faster? E or V? E is depleting faster. थोड़ा जागिए. Okay, E और V की बात कर रहे हैं. So V depletes R to the power 1, R to the power 2. So E depletes faster with the distance. Okay, if we make a graph of E and V, then how the graph will appear? E, the dip will be more. E will decrease more, V will decrease less. So the graph of E will be something like this. Okay, and graph of V R, its slope will be less. This is graph for V and this is graph for E. This is deeper and this is less curved. Less curved R1, this is R2, the value will deplete faster. So this is how it will be. Okay, now we come to another point. The potential, is potential a vector quantity or a scalar quantity? Answer, it's a scalar quantity, because potential is what? Work done on unit charge. So it is a scalar quantity. Because it's a scalar quantity, it does not have any direction and no unit vectors, I, j, k, no vector sign. Okay, then what does it have? Does it have a sign, positive or negative? Answer is yes. Like work is positive and negative, potential is also positive and negative. How work is positive? How potential is positive? So we will find out positive potential is here. From infinity I am bringing the charge here. The type of work I do decide whether the potential is positive or negative. When the work done will be positive, when the force and displacement are in the same direction. Here, if I bring a positive test charge and this is also plus, standard charge is plus. If I put it here, then bring it like this, I am applying force in this direction or in this direction. Plus, and what do I have in my hand? Q, and this Q is also plus. What is the natural force between the two? Repulsion. It is trying to go on this direction. So if I want to bring it here, I have to apply a force on this direction. So this is the direction of my force applied, and I am doing the distance, displacement in this direction. Both directions are same. So what type of work I am doing? Positive. So I am doing this positive work. I bring it here, 100 joule. I bring it here, 150 joule. So all these potentials are positive. Okay. See another sequence. I put it minus. This is minus. From here I bring the charge up to this much. Here I have plus Q charge. Can you tell me what should be the direction of force due to this minus? The force will be attraction. This will attract it and attract it up to here. I want that it should not go here. It should not get accelerated. I simply want to displace it from this place to this place. ये इधर भाग कर मत चला जाए. It should not run towards this. I have to stop it. So what will be the direction of my force? Yes, I have to pull it this way because it is having an attraction in this direction. It is trying to go in this direction. So I want to stop it this way and then allow it to move like this. I allow it to move. So what is direction of dr? This. What is direction of my force? Yes. How is the work done? Positive or negative? Negative. So I am doing a negative work. So the potential developed is negative. In this case, potential developed. In this case, I am bringing a positive charge from here to here. I have to apply force in this direction and there is a displacement in this direction. The work done is positive. The potential is positive. In this case, potential is negative because the work done is negative. Now, what is the difference between the two? Why here potential is positive and why it is here negative? I am the one who is doing the work and I am doing work on a test charge plus Q. Then why there is positive and negative? Because here there was a force of repulsion, I have to apply force. Here there was a force of attraction, I have to apply force in this way. Why it was repulsion, it was attraction? Because this is a positive charge and this is a negative charge, source charge. That means the sign of potential is decided by sign of the source charge. Is this point clear? So from now onward we make it a rule. The positive charge, the potential is positive when source charge is positive and the potential is negative when the source charge is negative. Okay, so we will remember this. And what is the quantity of potential? Quantity of potential is Q upon R. Put apart this Coulomb's constant. So Q upon R, you must remember, Okay, so if Q is positive, V is positive. Now, we come to the next thing, the potential difference. Can you tell me here, V2, V1, which potential is higher? I am bringing charge from infinity. First, it will reach V2, certain work is done. Again push it here, more work is done. So, which voltage is higher? V1 or V2? Can you make out? Again, what is potential? Work done. Here I have done work 100 joule. I go here, apply force, do the displacement, and up to this point the work done is 120. If work done is more, what will happen to potential? That will also be more. So, which one is larger, V1 or V2? V1 is larger than V2. Correct? So, I write here V1 larger than V2. Come here. I am applying a force like this, and there is a charge being attracted this way. The work done 100 this way. The work done 150. What is the sign of the work done? I am applying force in this direction because the charge is getting attracted. The force is in this direction, but the displacement is in this direction. So, the sign of work done is negative. Therefore, sign of potential is also negative. And here the work done is 100, here it is 120. But what is the sign? Which is the larger voltage? Very good. So, we have a result, V4 is larger than V3. Here, V1 is larger than V2. Okay, now see, I have got a test charge. I put this test charge here. Where will it go? Towards left or towards right? Test charge is a positive charge. According to Coulomb's law, this plus will repel it. It will go towards right. If it go towards right, it is going from V1 to V2. And what is V1? Higher than V2. So we make it a rule. The charge moves from higher potential to lower potential. Yeah. If I leave the charge here, anywhere, here, what is the direction of force? Attraction or repulsion? Attraction. Where it will move? From V4 to V3. This will move like this. And what is V4? V4, higher or lower? Higher. So the charge moves from higher potential to lower potential, even if it is moving this way. Here it is moving this way. But what is the common rule? It moves from higher potential to lower potential. If it is negative, then minus 100 is higher and minus 120 is lower. If it is positive, then 120 is higher plus 100 is lower. So it will move like this. And this is according to Coulomb's law also. So we understand it, make it a point. From higher to lower potential. Okay? This you will remember. Now, we come to the next thing, and that is relation of potential difference and electric field. How these two are related. At any place there is an electric field, say in this direction, dV is potential difference. At any location, this is direction of electric field and this is direction of R. This is dr. Now this point is A, this point is B. VA minus VB, VA minus VB is equal to how much? I am carrying a test charge Q with me. There is some electric field here. Because of that, there will be a force in this direction on the charge. I am applying force in this direction and doing this displacement. So, how much is the work done? F into dr, this is the work done. Work done from B to A. Work done from B to A. What is initial position? B. What is final position? A. So, what is the name of the potential difference? Final minus initial, VA minus VB. So when we write work done, how we will write it? From B to A, when we write potential difference, how we write it? Final minus initial. This point clear? Okay. And this is how much? F into dr. Why minus? Because dr has a direction in this direction and F is in this direction. These two vectors are opposite to each other. So minus. Right. Now, we know the formula for F. F is equal to Q into E. So this we can write as Q into E. But E has got this direction, not this direction. And there is an angle theta here. So E we can have a component in this direction. What will be component of E in this direction? Very good. QE cos theta. Right? This VA minus VB, we will call it potential difference as dV into dr. E cos theta into dr. Okay. Now, this dr, we bring it on this side. dV upon dr is equal to minus E cos theta. This Q, there is a mix up of the things. Let's make it this way. Work done from B to A is this, is equal to this. This Q you take on this side. So, work done from B to A per unit charge is this into dr. Is it okay? E cos theta dr minus Q we have taken here. Now work done per unit charge from B to A. What do we call it? Potential difference. Potential difference VA minus VB. VA minus VB, this is equal to minus E dr cos theta. Now if this we call as dV, then this dr you take here, dV upon dr is equal to minus E cos theta. So potential difference per unit length is minus E cos theta. This is the relation of electric field, intensity and potential difference in the direction of R. Potential difference in the direction of R. That means VA minus VB. Right? Not VB minus VA, because it is in the direction of R. So dB upon dr is this. Suppose E and R are in the same direction, then theta is equal to 0. If theta is equal to 0, then cos theta will be 1, and we will have a very simple relation, and that relation is E is equal to minus dV upon dr. Correct? Now this is a scalar quantity and this is a vector quantity, but this is a relation because E is along R. So this relation helps us a lot. We are going to use this relation a lot in physics, that electric field is given to dV by dr and potential difference. With this we can make it potential difference is equal to minus E dr and potential difference integrate. So formula for potential difference with reference to E, this is potential difference A to B is integration from this way. So this is the main formula you must remember. E is equal to minus dV by dr. Okay, now this also helps us to find out another unit of electric field intensity. Potential has a unit volt, R has a unit meter. So what is the unit of electric field? Volt per meter. Volt per meter. Okay, I am telling that the unit of potential difference is volt. What is 1 volt potential difference? We must define 1 volt potential difference. Okay, let's do it. You see, if we are asked what is the basic quantity, potential or potential difference, what should be our answer? The basic quantity what we define is potential difference. Only because difference is between the 2 points and 1 point we take in infinity, its potential has become 0. Then this potential difference is converted into potential of point A, because the other point has become 0. Like I ask you, what is height of this? At what height I am keeping it? You will see 3 feet. I say no, from floor it is 5 feet. You will say no, from the road it is 7 feet. So it also depends the height of a body, where is the reference point, where is the origin. And if we take origin at the center of the earth, or if we take origin at the infinity, then it will become absolute height. Same thing is for potential. If it is with reference to another point, then it is potential difference. But if it is in reference to infinity or reference to center of earth, then it is only one quantity, potential. In that potential, what is merged? Potential difference with reference to 0. So telling the whole sentence, potential difference with reference to 0, what we call it? Potential. It means potential difference with reference to infinity, with reference to 0. So unit of potential difference or potential, this is volt. Volt. Now, how do we define volt? What is 1 volt unit? So we go to the basic potential definition that volt is equal to work coulomb. Now, how can we define volt? The potential difference between the 2 points is amount of work done when a unit charge is brought from one place to the other place. This we have done, very first sentence. That is the potential difference. Now, what is 1 volt potential difference? 1 joule and 1 coulomb. There are 2 points in electric field in such a way that when we take 1 coulomb charge from this point to this point, we have to do certain work, and that work is how much? 1 joule. The points are so located that when we take 1 coulomb charge from this place to this place, we have to do certain work, and that work is 1 joule. Then the potential difference between these 2 points will be known as 1 volt. This is 1 volt. Please write it down. 1 volt is potential difference between 2 points. If 1 coulomb is taken from one point to the other point, work done is 1 joule. Then the potential difference between 2 such points is 1 volt. This is 1 volt. Now, can you tell me the dimensions of it? Find out dimensions of potential difference or volt. Work upon charge. Charge is what? Current into time. Current is what? I or A? A. Pardon? M, work done. What is force? And work done is, एक L और लगा दीजिए, ml2 t minus 2. So AT, this is ml2 t minus 1 A. These are the dimensions of potential difference or the dimensions of volt. Right? A minus 1, correct. T, this is 1T minus 3 and A minus 1. Yes, now it is correct. ठीक है? So ml2 T minus 3 A minus 1. Okay, these are dimensions of potential. So now we have got this relation. On the basis of this relation, can you decide the direction of electric field if we are given 2 points where voltage is given to us? Like these are the 2 points. Here it is 100 volt and here it is 120 volt. Q, R. What is the direction of electric field? Q to R or R to Q? Electric field, direction of electric field. You see, I will explain it by two methods, mathematically and logically. Logically, along the electric field you have learnt what happens to potential. Does it increase or decrease? Here, V1 is larger than V2. V1 is larger than V2. Large, small. What is the direction of electric field due to this plus? This is the direction of electric field. So direction of electric field is always from higher potential to lower. Here, this is higher, this is lower. Then what is the direction of electric field? In this direction. E. Because this is minus, this is the E. So, what is the direction of electric field? From higher potential to, and that is why the charge will move, because charge, positive charge always moves along electric field, and positive charge is moving from higher potential to lower potential. So, electric field is also from higher potential to lower potential. Okay? That is one thing. Other thing is, we have known that E is equal to this is direction of E, this is direction of dr, dv, VA, VB. No, we will have to explain it on the basis of dv, dr. They are opposite to each other. No. Okay. In which direction potential increase? Yes, we were right. In which direction the potential is increasing? V1 is higher or V2 is higher? V1 is higher, correct? V1 is higher than V2 because this is direction of E, and here is the source charge. Therefore, this R is less, this R is more. V1 is higher than V2 here. Same thing. Okay. Now I stand here. Tell me, in which direction V is increasing, towards left or towards right? V, potential is increasing. Here it is increasing or here it is increasing. Which is higher, V1 or V2? V1 is high, V2 is low. So what is the increasing direction of V? Left or right? Left. What is direction of E? Right. So direction of E is opposite to the direction of V, potential difference, dV. Understand? This is higher potential, nearer to it, this is lower potential. So dV is in this direction and E is in this direction. Therefore, if we want to make an equal, what should we put here? Understand? What does this minus says? Yeah, the V increase in opposite direction of E. That is the significance of this minus. So you should remember this, and let's write it also here. Negative in E is equal to minus dV by dr. Negative sign shows that potential difference and electric field have opposite directions. Now you understand what is meant by opposite direction? What we have taken as direction of potential difference? Lower to higher, increasing. Okay, so these are certain relations between E, dV. This is a very important relation. On the basis of this, I would like to ask you something. No, let's first do equipotentials, then we will do that. Okay, after this we would like to do potential due to more than one charge. So far we have done potential due to a single charge. And what was that? Q upon R. Now we will see if in a place there are more than 1 point charge. More than 1 point charge. There may be 2 charges, there may be 3 charges, there may be a system of charge. How do we calculate potential because of that? See, potential due to multiple charge. Okay, multiple charge. If there are more than one charges, these two charges may be positive and negative charge. This may be both positive charges, both negative charges, and this may be one positive and one negative charge. Anything. Okay, here is a point. At this point, P distance R1. This point P has a potential. How much is that potential due to plus Q1? Answer, V1 is equal to Coulomb's constant, Q1 upon R1. Now we have a charge here, Q2. This is also having electric field around it. This is also falling in the electric field of this Q2. So this point is also having a potential due to charge Q2, due to electric field of Q2. How much is that potential? R2, V2. This is C. Right? Now, how much is the potential this P has got? Both are coming from the different direction. Does it make a difference? Answer, no, it does not make difference. And that is the convenience and beauty of the potential. Why? Because potential is a scalar quantity. No direction, no vectors. So for addition, what we have to do? A simple addition. So what will be the total potential here? Net potential V is equal to V1 plus V2, and this is equal to this. Suppose this is minus, then we will put minus here, and V1 is equal to Q1 upon R1, V2 is equal to minus Q2 upon R2. Right? So write it down. The potential at a point due to multiple charges. I will write it here. Potential at a point due to multiple charges is algebraic sum of potentials due to individual charges. And this is what algebraic sum. Algebraic sum means we have to take plus and minus. Understand? So if it is a positive plus, if it is a negative charge, then it is minus.